have no idea why this happens. Anyway, welcome and hello and welcome, yeah. So I want to add Steam here to the page, to my contacts page, because I guess why not? Just, I don't even know if I can. Well, maybe I would have checked. Also, Steam.com doesn't exist. So yeah, I would have been sad. I would have probably checked, but thankfully you did. Anyway, oh my god, login. Okay, I'm gonna do it after the stream. Then. So yeah, here we are. Hold on. Let me get the overview. So last time we've completed about this part, the green stuff, and now we are allowed to do 3 levels. 1 of 3. I think let's go with this one. This model of brain size being the main predictor of intelligence was naive. Tool making and usage is key in the early evolutionary stages of developing intelligence. Therefore, the number of arms on a creature is clearly the main predictor of intelligence. Did you know there are sea creatures from your planet with 4 times as many arms as you, and they are doing better in tests? Not each bit of byte input. Byte note. Okay, bitwise note. So yeah, I don't think I need to give a reminder on this game, because yeah, probably do remember. Now, let's do. I wonder what happens if I take white, for example. I'm just. So it's the same color. Okay. Okay. So a bitwise node should be easy, right? Where's the node? Oh, and I need to scroll, and now I can place 8 of those. Can I actually place them compact enough? Yes, I can. That feels powerful. I should hold shift. Now I wish I could route so many contacts at once, but I guess I can't. Fortunately, we'll have those byte operations. So yeah, fortunately, once I build those modules, we'll have those byte operations, and I won't have to do this again. So why is this flipped? For whatever reason. Well, whatever. What if I... It doesn't really matter. Okay, so play. And it works. Byte note, yeah. So I get the byte note element. Now we do actually have to go to memory, and yeah, let's see. Delay line. 1 tick later. Circuit that outputs the same as input, just delayed by 2 ticks. I guess they'll give me this as a 2 tick delayer or something. Oh wait. Well, this is pretty easy, right? Now, in the previous level, you learned how we don't allow circular dependencies. Hold on, where did they go? Yeah, here. Now. Yeah, we'll have to do one of those. By the way, I wonder what this is. Bit switch. Odd ticks. Okay, let's do ticks first. That allows circular dependencies. Now you must learn the one exception. The delay line is allowed to depend on this input. This is because the input does not influence the rest of the circuit until the next tick. Square pins in the game never affect the output in the same tick. They therefore never cause circular dependencies. Output this on even ticks and this on the odd ticks. Okay, this is interesting. Now I think I need... how was this flipping stuff? Oh wait, I can just... Yeah, wait. I can just note the input, right? So this thing is gonna output this. Okay, this works. A manual entry on circular recipes. Okay, let's go to bit inverter and let me read the manual. So yeah, we have quite a few manual entries now. Oh, this is SR latch. Another version of SR latch. And what is HR latch? I don't even know what this is actually. So yeah. Oh, and there are links, wow. But yeah. Doesn't really matter. Cause I know this already. We're experimenting with how backgrounds influence cognitive functions in Earthlings. I noticed that the background changed, to be honest. So when an invert is 1, output the opposite value, otherwise just output value as it is. XOR? Just literally XOR. Like, I don't know what's the point, but I think the different background, I just like it. If I define the background, you figure out that this was just XOR gate in disguise. Well done. Now, I wanna do this one. And I mean, I don't have a choice, but yeah. Now, what is this? Switch. Oh, it's switch. Hold on, is this a transistor? If components output different values on the same wire, you get an error. However, the same components have some components have gray output pins. These are not outputting at all when the component is not enabled. This is the case for bit switch component. Well, this is just an AND. An AND. A regular AND gate. Is this output is disabled? This means that more than one... Well, actually not quite. So yeah, this is the switch. Build an XOR gate using 2 NOT gates and 2 switches. Okay, that's interesting. Oops. I kind of oh, by the way, Control Z works. Also, I can't move this. Okay, so I need an XOR gate. So I need to make an XOR. How do I make an XOR? Enable. By the way, this is useful. A pinout diagram. Okay, so we note the input if the second. So we output. Okay, so let's just do a selector. So we either output a regular signal or the inverted one based on this one. So if this one is 1, then we output the inverted. Hold on, let me switch the color for control lines. So then the output is inverted. Else, so here I'm gonna put a NOT gate. I'm gonna do this, and now I can connect this up. Also, I would like to move this a little bit. Well, this is pretty insane. But yeah, this is an XOR. Unlock switch and 8-bit switch. Well, that's actually useful, you know. A high impedance state and wires, and now I have only one level to do is this one, 18 bytes. Oh my god, are we getting a 2-byte adder? Well, just an adder, an 8-bit adder actually, or 1-byte adder. Add 2 input bytes. Each output bit in the output should be a result of the addition of the corresponding bits from the input and potentially a carry. Continue. Not fit in 8 bits turns the output carry. You can think of it as 9 bits. Find that there is an input carry as well. It's useful for chaining together byte address at large numbers. You can use this hint to get stuck. I'm not gonna use the hint because, well, obviously I know what to do. So we need two of those. Oops. Two of those, obviously. So 8-bit, 8-bit decompress and compress. Also, I should switch color to this one. So back. Yeah, 8-bit maker and a byte splitter. Now I need to. Hold on, what's this? Oh, 8 is that's A and B, so I need another one. How how did I do this? Okay, so we have another switch. Let me move this. Yeah, okay. Now also we have carry. Right, this is a carry. And this is those are inputs. Alt click to move wire head. Oh. No, I don't need that. So I had a half adder and a full adder. Okay, I need a full adder. And what a weird shape. Okay, so we add those and the output is a 1 bit. Then we do, okay, let me do 8 of those. 2, 3, 4, 5, 6, 7, 8. So this is carry. No, this carry goes here, just like this one, and so this one goes here, this one goes here, this one goes here. Wire up the carry. So there is actually fast carry. So it's not like regular computers don't normally use this, I think, because so well in 64 bits chaining carry bits is not efficient, and you can compute carry faster somehow. Not sure how. Maybe we're gonna get to this, maybe not. Who knows? So 2 comes here. 4. Now let me just wire the second one first. Faster. Okay, I can undo, that's useful. Especially here. But I think that is it. I think that's a full byte adder. And it seems to work, you know. Yeah, I think it tests all of them. All of the combinations, yay. So we've unlocked an 8-bit adder. A whole adder. Now we've got two things. Negative numbers, which is 2's complement, which is cool. Unlock something unknown. I wonder what this is. Might be like just 2's complement as a feature. And then we have input selector. The bus saving gracefully. I guess this is an SRH saving bytes, byte H, and then yeah, we're gonna get to the CPU architecture level. But first, yeah, I think I'm gonna continue on with the ALU part, with an arithmetic part. To know the difference between things you need. To know the difference between things you need subtraction. To get subtraction, first you need negative numbers. Yeah. Continue and okay, yeah, negative 128. By the way, I did not know you do this. I know that you, in order to invert 2's complement, you just invert all bits and add 1. I think. Well, this level introduces 2's complement is the most common representation for negative numbers. Here the highest digit is negated. For bytes, this means that 8-digit changes its the 8th digit changes its value from 128 to negative 128. You finish this level when you get to level 3 and beyond. here for timeless accessibility mode. Okay, let's rate it race. 15. Oh, it doesn't. Okay, this is gonna be a bit hard. -3, -14. Oh my god, this is gonna be a bit hard. -7. Wait, it just messes with my brain. -13. Hold on. -2 again. -15. Here. -23. Okay, cool. I feel like I'm doing it random. I mean, I know I'm doing it pretty much randomly. Okay, -3. Okay, I need to do this. -5. This, -20. Okay, there is a pattern. I mean, it's not complement. Oh no. I mean, I've reached level 3. That's the only thing that matters. To go between the negative positive, you flip all the bits and add 1. Yeah, I know. Highest bit is 1, the value is always negative. The byte adder bit also works with signed numbers. There is still only exactly one way to write each number. Yeah. Unlocks a manual entry and negative numbers. Toggle between signed and unsigned. Okay, so we have signed negator. Oh, let's do this, but first I want to see the manual entry. Oh, negative numbers, or what is it? Binary, bytes. Oh, here it is. I mean, that's boring. Another interesting representation, perhaps worth looking up, is base -2. Okay, that is interesting, but not today. Taking the input as signed where 8 bits is this make a component that takes a number and negates it. For example, 4 negate would become -4, 9, -9 negate would become 9. Okay, I wanna do this in the best way possible. Mass logic. Oh my god, it groups stuff now. It groups stuff like crazy now. Okay, so we need a negator. I know how to do it really fast, but I want to. Like, I know how to do it in a really easy way, but I wanna try. By the way, toggle number format. So yeah, I could do it the easy way, or I could do it hard way around. Which is what I choose, and I think. Okay, so how do I? Is there a half header? They took away my half header. Okay, then I don't care. Okay, I'm just gonna do math adds and logic not 8-bit not. So we flip it. And then we add 1. So we add an on signal, which goes into carry. So this is, and this is the output. So yeah, since this is unused, it could be more optimal, but I guess sure, whatever. And I think this should work. Yes, it works. Yay. Now, okay, now I've got to advanced memory. Okay. Even though he did not pass our test, we decided to keep the dog. Unlike most Earthlings, he is fluffy and follows simple instructions well. We might want to team you two up, since you complement each other's shortcomings well. What does this mean? Okay, so this is an input selector. When byte selector input is this, output byte A, otherwise output byte B. Okay, that's pretty easy. That's just. Oh wait, they took away the bit switch. No, they didn't. There's just no logic part for some reason. Well, this is easy. I just need those 3 components. So this is just a selector. We did this with XOR, right? We did this with XOR before, so we connect those two up, and then we just select the right one. So we take this, and then we also do a negative here, and then it just selects the number, except that I need to flip those. Okay, sure. Hold on, why did I remove the negation? We're not. Ah, hey, let me grab you. Okay, let me do the not first, then here, and then this goes here. So then this works, right? Yes. Well, it's easy. Input selector component. Hold on, does it say MUX multiplexer? Also, we have to do those two. Saving gracefully and the bus. I think that unlocks a latch. This level has 2 byte inputs and 2 byte outputs. Your goal is to copy from one of the inputs to one of the outputs. Oh, wow. The first bit input determines which input you should copy from. The second bit input determines which output you should copy from. Okay, so I need to take... Oh my god, I only have 2 nodes and 4 switches. Hold on, this is it? Yeah, this is it. Now, I mean, this is easy, right? Yeah, this is easy. So this one is the input, this was the output, right? Well, this is just a multiplexer again. So I assume we take I assume inversion works the same. So here's one, here's gonna be the second one. So we go do this and we switch it here, and then we just do the same thing, quite literally. Actually no, I'm gonna do this and I'm gonna wire it like that. I mean, it's still off center, but sure. Now we need to negate this signal, and I assume it will go this way, but I'm not sure. We'll have to test it. Okay, no. Oh wait, I'm dumb. Okay, let's move this back. I forgot to connect the outputs. So yes, this goes here, this goes here. Row 1, row output 0. Okay, so we need to swap those. Okay, good. Now this works, right? Yes. Unfortunately, it doesn't unlock the component for some reason. Because this probably would have been useful. Actually, I mean, maybe not. The delay line only allows us to save a value for 1 tick, but sometimes a component can save sometimes a component that can save values for longer periods of time is useful. We want you to build such a component. In this level, you have 2 inputs. When the first input is 1, update the saved value. The second input is the value. Always output what is currently saved. This is a diagram of the component you want to build. Okay, save enabled, save value. Okay, what do we have here? We have the whole system. So yeah, I know how to do an rest latch. This is actually a D latch, I think. I mean, in the book I read, it was called a D latch. By the way, backgrounds keep changing, and I like this. Now, how do we do this? I mean, I can just do a loop and then select. Do I have a selector, a 1-bit selector, like... Come on, I have a MUX, a multiplexer. I don't have a single-bit multiplexer, why? Okay, sure, I guess. So, hold on. I guess I need 2 switches. One is gonna be... Oops. So one is gonna allow me to... loop the value. This one is the default one, which means we need to power it by default. And the other one is gonna let me write the value here. Also, this was placed for me. Yes, but I removed it. Now I'm gonna move this here and this here. This is right, huh? No. Short circuit. Oh wait, this is short circuit. How do you stop it? Okay. Hold on, okay. This outputs save and value desirable output. Oh, okay, this changes a lot of stuff. Well, I mean, not that much. So we do actually want to output the last tick. So let's simplify stuff. Let me get two switches, and then let me get a note. Now, so I either want to let me do a multiplexer, a classic one, which is gonna one input is gonna be the output, and another input is gonna be the value. And now, if this is false, then we'd want this. Else we'd want this. Okay. So that's a latch, right? Yes, it works. Unlocks a 1-bit memory. Why have you called it a 1-bit memory? I don't know, but it's a latch. They didn't even suggest me looking up an RS latch, etc. You know. Anyway, saving bytes. This unlocks a component, right? Create a circuit that can save or load a byte. When the first input bit is 1, load memory and send it to output. When the second input bit is 1, save the input byte. The output has an enable pin, enabled only on load. What? Okay, that's an interesting thing. So I think this is like a load one. I am a bit confused by how it works. Also, it doesn't show me the diagram, unfortunately. Oh wait, I can see. Input 1. It's 0, so don't load. This is so load. I wanna know how on earth the output works. If I enable this and see output, okay, that is interesting. Oh, so this is a toggleable output. Interesting. I know why I need that. So we have 1-bit cells, 1-bit memory. So I should have probably taken a handful of those. 3, 4, 5, 6. I'm gonna do 6, 7, 8. Or actually, I'm gonna move. I can't really move them much. Let's just spread them out a little. Well, I'm not really spreading them out, but yes, doesn't matter. So yeah, 8 bits. How does this work? Save enable, save value. So let's do. Okay, this looks bad. Should just probably move them down here. And yeah, I know it's chunky, but trust me. Actually, you know what? I can do this, right? I can do this, and it's gonna be more compact. I just want to it to fit on the screen better. Okay, 1, 2, 3. I think the output is a switch, so I don't have to put a switch there. Here. Oh, now I need to put Inputs, hold on, that's save enabled, right? Yes, it's save enabled, and this is the value. This is gonna look interesting. I think I should switch to blue for control signals. So this is a control signal to load, and this is a control signal to save. Yeah, this is gonna be fun. Wiring alert. Here. Here. I think that's right. Okay. Short circuit. Okay, no, it's not right. Okay, now you know. Now this is kind of hard because of short circuits, right? Because of how this wiring works. But I guess I can do this, and it's gonna be fine. Yeah, I can do this because, well, how wiring works. So I might as well do this then. It doesn't let me. Well, actually, I know how to make it let me. It's not really what I want, but action load and save. Desired output. The state 17. Desired output 17. It outputs 1. So both are 1. Input 2. So now you wanted to go the opposite way. Now you want the immediate way. No, well, actually no, you don't. The value is 1. It's expected 17. Why is it 1? Might have messed up something. Okay, let's do first load save 0. Action save. So we're saving 17, so this is 2 bits. Those go to values and save goes to 1. Oh wait, this is disconnected. Now, that's better. Okay, this unlocks an 8-bit register, finally. Well, that's important. An important milestone. Now, we are pretty close to ending memory, a counter, and a little box, whatever this is. And this unlocks the component. But first, we're gonna finish arithmetic. Create a component that can switch a signal between 2 pins. 1 bit oh, you mean... So you mean this? Okay. So this is the second bit. Well, this is the second bit, and then the first bit is just an inverse bit. This boss high. This is Turing Complete, the game. We're playing it for the second stream. This unlocks a 1-bit decoder, whatever, why ever I need this. I don't know. I mean, I guess the decoder would have been useful previously, probably. So yeah, this is Turing Complete. We start with logic gates we start with this. And then we create logic gates, like, this is NAND. And they're giving us NAND. Only NAND. Then we make a NOT gate out of this. You know, NAND logic probably. A NOR gate, etc. So yeah, we've made simple gates out of this. Then we make this is just a teaching level. So we make this is also a teaching level. Okay. Which one gave us a new component? It's still 8 lines. So this one, for example. Oh, that's just a doubling circuit. Hold on. Where have we made another? yeah, this one. A full as 8-bit adder, for example, made out of logic gates like byte splitters, etc. Then we have memory, so this one gave us a D latch. Well, I'm calling it a D latch because, well, I'm used to it. It was written in the book this way. So yeah, this is just a latch which we have save and load signal, save and value signals, etc. Virtual circuit board, very simple. It's not electronic, it's just logic. I mean, this is also just logic, except that it does have a switch. Okay, so yeah, we just completed a 1-bit decoder. Now I want to finish arithmetic, and yeah, and I can do that. I want to finish arithmetic first. With 3 bits of input, there are 8 combinations. Make a circuit that selects one out of each of the 8 combinations, no more or less than 1 bit should be at one at a time. By the way, I forgot to mention Fizzbuzz that if we go here, this is a working computer. This lesson lets us create a full working computer, and then we program it using assembly to solve our own programs. So yeah, that's a fun game. That's basically why I bought it and playing on stream. Anyway, so this is just what is this? I never saw this output. 4-bit outputs. Anyway, so yeah, we've got a 3-bit decoders. And did they give me a 1-bit decoder? They did. Should I use that? I'm not sure how. I'm not sure how to do this with hollows. Oh wait, I'm just selecting this color. Okay, so. I mean, I can just do it in a brute force way. Yes. Okay, let me think actually. So we need on 0 we need to output to this one. Okay, so let me get a few switches. So yeah, this is a switch, and like what's separating this from just logic is this kind of output. So you can connect those together and they won't be shorted. This is basically a transistor, kinda. Okay, so if this is 0, so I wanna decode this second one. I think this is gonna give me an 8-bit decoder instead of a 3-bit one. Because it would make sense, because, well, actually an 8-bit decoder has 256 outputs, so not sure about that. Okay, so let me use 3 decoders. Well, those are just NOT gates inside, but they're easier to use. Now. So we have 8 combinations. If this is 0. Oh wait, okay, so start with the later bit also. Can I see? Okay, so the third bit when it's 1, we want to go from 4 to 5, 6, 7, 8. So we want to select the second half. I wish I had like 4-bit selectors here, 4-bit switches. I mean, I have 8-bit switches, I could use those. Yes. So I need to decode those two, and then multiplex it on either this output or this output, right? Using the decoder. So it's the 8 switches alone. Yeah, this is a bit of stuff. And yeah, I have an 8-bit switch, but I don't want to use it. Also, it requires 8-bit stuff. It's 4, 1, 2, 3, 4. Okay, so we need to decode this one. This is the same principle, I guess I can apply. So 1, 2, 3, 4. Hi, Cuban. Thank you for the raid. Gordy joined the community. Oh my god, overall is gonna lag. But yeah, you've got your own plushie. Good to be happy. So yeah. As I was just explaining here, I wonder if I re-enter, it's gonna reset. So we're playing Turing Complete. The game where, well, you can see the map of completed levels in green, and yellow is what we can play right now. So we're starting with wires and making logic gates and not out of NAND, etc. We build out what should I so a half adder, for example. Then we build out like more stuff, a full 8-bit adder, latches, and so eventually out of logic gates we build a working computer, program it in assembly, and well, continue on with programming it. So this is the second stream, and we're here on a 3-bit decoder, and this did not reset my progress. Okay, that's good. I was kind of worried about that. So yeah. What I'm just doing here. And a 3-bit decoder, what here we need to, well, basically decode the binary number into one of 8 possible outputs. And yeah, we've done this for a 1 bit, as you can see here. Okay, so let me. So the idea I have, and I'm pretty sure this is how it was supposed to go, is we decode 2 bits and then we multiplex it on either the first half or the second half. And for 2 bits it's the same way. So if this is 1, we need to connect. Okay, this is gonna be a bit messy wiring. Hold on, that's an extra one. Those 2, 3, this. So this 4, this block of 4 is gonna be this one, and this block of 4 is gonna be this one. Now we need to decode the 2-bit one. Oops. We switch back to this one. It's colored. Now I just do the same. By the way, music is built in to the game. I hope it's not copyright. I didn't actually check for copyright strikes, and I think this is what we need, right? Yes, it works. Also, this has a storyline. They are killing everyone who can't build a computer. Whether internet disable bit to this component. We tried. We were tired of looking at him running in circles, and we're looking for other pointless and tedious tasks to give him. So now, yeah, we've got a 3-bit decoder with a toggle bit, or whatever. So yeah, that way we've got a component and now a logic and oh my god, what is this? Create a device that can OR, NAND, NOR, or AND 2 inputs. The shared input will be the instruction. Oh my god, we've got to an ALU state, except that we don't have addition and subtraction similar. You can move the right components in the level for reasons that will be revealed later. Okay, I know why. Okay, so normally in levels we can move inputs, but here we can't. Probably because in the future the size of this component is gonna matter. So I can't move inputs to make up more space. Now, OR, NAND, NOR, or AND. This is the instruction. Code. Okay, hold on, this is the instruction, right? Yeah, this is the instruction, and it's an 8-bit value, so we need to split it up. Also, where did it go? No. We're actually... So we also have 3-bit decoder with an enable, or actually disable switch. Ha! An inverse enable. Okay, sure. Now we have I wanna know if OR, okay, this OR I am messing up. Oh wait, this is negative. I think negative. 128. What's the state? What are the instructions? Hold on. I can't quite figure it out. And I can't run it. Okay, this is end. Why is this end? Why is this end? Or, oh wait, this is the first bit. Okay, that makes sense. NAND and NOR. Okay, so this is OR. So we need to make it small. And I think we don't actually need the decoder here. So we switch to NOR, switch to NAND, and both are to AND. So if, by the way, this also has a manual where we have information. And if you look at De Morgan's law, so we can invert the input. By inverting the input or output of logic gates, we can, well, get a different kind of logic gate. And maybe, so this is, so by default is OR. Horizontally. Yes, so this bit switches, flips the thing horizontally, and this bit flips the thing vertically. So we have an OR here, this one, and then if we toggle this bit, we go to the NOR, which means we invert the output. And then if we toggle this bit, we go to an AND, which means we invert the inputs. So 2 bits, and I guess we can, well, we can just do XOR gates here. Where do we have XORs? Also, is this? Yes, this is a byte input. We have byte utilities here. Also, I don't have. Oh wow, I only have OR and a NOT. How convenient. I mean, I don't actually need a NOT. I need an XOR actually. Or I could do a multiplexer. Yeah, I could do a multiplexer, which is just a switch. So if this is 1, we route the second one to this, and if this is 0, we route this one to this. So if I get NOT gate, also I can move this here. So that's I want to reduce the footprint as much as possible because, yeah, I assume it's gonna be important. So multiplexer. So we take this route. So by default it's OR, which means we're selecting this one. So and then we also note it. So here, if this one is 0, we take this. We take the 17. Otherwise, we take the inverse of it, the binary NOT. I mean a bitwise NOT. Then also we take. Hold on. I need another NOT and another multiplexer. Then we take the second bit. Hold on, actually. So this one switches. So I invert the input is this bit. So this inverts. Yeah, this it's right. Now take the multiplexer. Also, I should probably move it here, just to come back, just to make more space for the wire. Now we take the multiplexer again, and we take this input. So I should have what? Okay, so we multiplex this into OR, into an OR. Can I move this? I probably shouldn't. Now I can just route it here, and now I can just put another multiplexer and another NOT. So we flip the value as well as we don't. Okay, one thing for sure, it's gonna be the output. Also, the bit flips it. So if it's 0, we just take a regular value, and if it's 1, I think I can do it like that. and if it's 1, we flip it, and this should be it. Yes, it works. This unlocks an 8-bit AND, an 8-bit NAND, and an 8-bit NOR. Well, that's interesting. And it didn't give me the components. By the way, live quick, come back. So it didn't give me the component I just built. Sure, we're gonna build another one. Even cooler than that, I'm pretty sure. Because, well, we'll need an ALU. Now, we've completed the arithmetic part, but there's still 2 more lessons for memory part, and they give us some components. Counter first. Counting is so fundamental, even insects do it. From counting, species can evolve to compare and do arithmetic, and before you know it, you have apes building computers. Make a divided counts or increments once per tick, so that's like normally I would do it using T flip-flops. Again, I've read the book on logic components a while ago. 2 inputs, a bit and a byte. The bit input should toggle between counting and overwriting with the value of the byte, huh? Input. Okay, add 1 to the counter or overwrite it. That is interesting. So we need to store the internal state, which means a register. Memory, by the way, this gives us... I did not know it's gonna show the register's memory, which is interesting. So we have load, we have save, and we have the value to save. So the value to save is here. Wait, hold on. Input is for overriding, I assume. So if this is so if this is 0, we count. If this is 1, we override it. Hold on. Actually, I probably need a multiplexer here in order to save the value, and then so there is a way to increment a value. There is a better way, but I'm just gonna take an adder and route 1 to the carry bit, because that's the easiest one, because I'm not gonna rebuild the whole adder again. So we either take we either take this value, which is when this bit is 1, to store, or we take this value plus 1, so we move it here, and yeah, plus 1 is oops, plus 1 is this. Now this is the output. Yeah, this is the output. It goes to multiplexer, and now the write signal is always on. The load signal is always on as well. I assume that's how it will work. And this works. Seems like it does. I wonder what happens if it overflows. I mean, I guess it will just overflow. I mean, actually, yeah, it's just gonna overflow because I left the carry bit hanging. Also, this gave me a component. This gave me an 8-bit counter, huh? Right? I mean, I can't see it here. And I probably won't be able to see it here. Can you fit 4 bytes of memory in this limited space? Continue. So you have to build a circuit that can save or load from 4 different bytes of memory. Again, one bit determines if you save and load, and another bit determines if you are save. One bit determines if load, another bit determines if save, and comes with a corresponding value. Additionally, you have 2 address bits. Little box. So this is just a... Oh, sorry. Got too excited. Here. So this is just a 4 byte memory. Also, we have 128 tests. And if I I should probably move this somewhere. So if I move it like this, you can see we've got 128 tests, address, section, well, this doesn't really matter right now. Library. So input, load, don't load, save, don't save, and the address. So we have input, 2 inputs. And why did I need 2 inputs? Oh wait, this is the address and this is the input. Yeah. Now, we need to actually do this. So 4 bytes, and also we've got a very limited space. 4 bytes is just for registers, I assume. Because, well, building other way, but building memory in any other way will be not efficient. Also, I wanted to drag shift around it. Now we need to select the right output. For that we have a multiplexer. Or actually, how many? I need 3 of them. Unless I have an actual. Yeah, I need this, and now I also need a decoder. Or actually, I don't need a decoder. Having a multiplexer, I don't need a decoder. Yeah. So 2 multiplexers. Oops. I constantly do this accidentally. Also, what is this? We have an output enable switch as well. So we do this first. This is the output of a multiplexer. Then we route 2 multiplexers into this one. And in order to select them, so first bit selects A, B. Okay, so we have A and B. Well, actually, it doesn't matter which one we select, to be honest. This selects A and B. This one is 0 and 1, so we're gonna do this. Now we're gonna do this. Oh, also I need to do inputs. So I do need to actually decode this. But I mean, there's. Well, okay. So if I do need to decode this, I'm actually gonna do this with 8-bit switches, 4 switches, and we have a 3-bit decoder somewhere. Don't say they took it away. I mean, I don't really care. I can do 1 bit. Or I could do a multiplexer. Actually, you know what? I can do a multiplexer on both sides. So I can undo this. Okay, so this is a multiplexer on output, and we're gonna do a multiplexer on input. I think we had one. We had a 1-bit selector. Why did they take it away? Okay, sure. We've got switches. Can do it both ways. Okay. So we need a safe signal, and yeah, this is a safe signal. Load. Oh, we also have a load signal. Actually, you know what? We don't need this. We do actually need a decoder. But since we have separate load signals, this how it normally goes in electronics, we can just connect those 4 together and just short it to the output also if I don't want to move it. I mean, doesn't matter. Also, we need an output enable, and so first one is don't load, don't load. So this goes here. And also this goes, well, yes, it goes here. Now address. I need to decode address into 4. So if okay, let me think. Need need switches, right? Switches. So I need 1, 2, 3, 4 switches. So this one is gonna select those two. Oh wait, this one is gonna select those two. Now, hold on, like it's wrong. I mean, I could have replaced those by AND gates, I guess. Also, wrong. So this, and this. Okay, yeah. So we decode the first input, split it into two, and so we selected it or the other one, depending on this one. Right. Now, so we do load. We always load. I'm gonna do always load. So I'm just gonna route these two loads. So only the one that's selected is gonna be loading. Then we have one for save, and for save I need an AND. Where is the AND? Here, regular AND. Oh my god, this is so big. You know what? I don't need an AND. I need a switch. A switch is basically just an AND. So I can't put it here. So I need to get rid of those wires. They're too big. So yeah, I can use a switch instead of an AND. It's just fine. So I'm gonna route those to saves. This is the value to save. Okay, this is gonna be fun. A fun routing challenge. Also, I'm gonna remove those. This one first is a load bit. I don't like how it goes. So I just want it. Okay, it's not gonna. Let's connect it first. So this one goes here and here, and this signal. Okay, let me just connect those. So I'm gonna connect. Okay, it's a bit confusing. So yeah, we've connected all of those outputs to the two inputs of those selectors. Then also let's connect to loads as well. Yeah, it's connected here. Now let me just do a different colored line. So this is all of the save. Then load. It's gonna go here, but first I wanna connect the values. Oh, and so I wanna connect this value. Okay, don't care about how messy the wiring is now. Let me just short all of those and short this and connect this. I mean, this should be it, right? And it seems to work. In our advanced civilizations, forcing prisoners to do extremely menial tasks is slavery and technically illegal. This is why we instead had our intern create the 256-byte version of your component. Okay, so we've built a 4-byte memory, and now we get a quarter of a kibibyte memory for free. Instead of slaves. Okay. Now we've got a 256-byte RAM. That is cool. And with that we finished memory, and now we're actually going to build a working computer. And you know, I'm gonna continue. So yeah, wow, programs. Yeah, it's gonna be fun, you know. Also, this gives me a manual entry. Arithmetic engine. Also complicated to you. What? I mean, this was a bit complex. Maybe I should try my best to explain it. So this part of okay, so we've got a decoder, which if a bit is 0, this one is 1. and this one is 0. If a bit is 1, this one is 0, and this one is 1. So we just toggle it. You can see here. Oh, I can't zoom in anymore. So you can see this one is on. Now I click and this one is on when this one is on. So this is just a selector. Now with this one we route it here. So this is basically a 2-bit address. I mean, this is actually a 1-bit address. So if this is 0, we select the first byte. If this is 1, we select the second byte. Now we route it to this. So here and here, and we also route it to this. So those are switches. And then we have a similar decoder, which if this is 1, it's gonna enable this part. So if those 2 bits are gonna be passed through these 2 switches, and then they're gonna be passed forward. And if instead this one is 1, it's gonna select those 2 switches, and those 2 bits are gonna be passed through those 2 switches, and those 2 switches are gonna remain zeros. Then we just pass those signals into 4 registers. Each register can load, save, and output a value. I still don't understand, but maybe worth trying. Then we've got 4 more switches. So apart from those 4 switches basically output a 1 for whichever register we select. And then we route this one to a load. So whichever register we select is gonna have its load enabled, and all others are gonna have their loads disabled. Then so we have those 4 switches which basically just take those 4 inputs, and if this save input is 1, they're gonna pass those 4 inputs forward. So they're gonna pass the save signal. So the one that has a load signal is also gonna get a save signal if a save bit is 1. And then we have also a load bit, which, well, all those 4 are one of those 4 always has a load bit on, and this load bit just stops whatever one of those registers outputs from going out of this component. That's probably a bad explanation, but anyway, registers. Hold on, we've got registers. Why are you telling me another registers level? Okay, fine. Okay, this black screen scared me a little bit. Time to create your master project implementing the Overture computer architecture. This will be an actual Turing Complete machine, a true computer in every way. I want to know what Overture is. Overture. Overture. State of art performance. It was nice. You're actually a lot behind because stream latency. I mean, it's fine. I know about stream latency. I don't know. Oh, I've dropped 5%. That's painful. I've switched to 30 FPS, by the way. Not sure if this is gonna help, but yeah. What is this? It's probably not what I need. ISA. Overture 3D printing filament, huh? Steam community guide default instruction set architecture. What is this? What is this? Why is it discussed on Steam? Oh, it's because it's discussed about this game. So yeah, Turing Complete, by the way, I should have probably mentioned Turing Complete game. And also there's my profile on it, which I don't really know where to find. But anyway. So yeah, we're not gonna read an explanation. I guess this ISA is just invented by the guys here. So I have logged the red components of this level in place, since you always make a mess and don't leave enough space. The mess you make from now on is saved between levels. You'll no longer get to start fresh each level. Yes. Now you can see that when I make something here, how messy it's gonna be, it's gonna impact whatever. You see the custom thing, Alt C. What is that? No components area. Huh? Alt components level input, level output. Wow. Level screen and 256 byte RAM. Wow, that's cool. Anyway, so yeah, now we've got to make this small, because the smaller it's gonna be, the smaller the components is gonna be, and the easier we're gonna be able to use it in other components. In this level, you need to create a circuit which can copy from a source to a destination. The instruction byte in this level determines the source and the destination. Bits 1, 2, and 3 give the destination, bits 4, 5, and 6 give the source. Source and destination can be one of 6 registers. We'll name them Reg 0 to Reg 5 respectively. Additionally, the map has a dedicated input component which can be source and output component which can be destination. Okay. So source, this we have input and this we haven't used. Destination we have this and output. So I can copy from one register to another. Well, this is interesting. This is kind of close to like the schematics I drew as a child, as a kid. I was like, I had a A4 piece of paper. I just used a pencil and a ruler to draw schematics of imaginary computers. This was a fun childhood. Because I always wanted to do this, and now I'm here playing Turing Complete. To get a more intuitive understanding of the requirements, click the instruction icon in the upper left corner. Okay, I wanna know what the instruction icon in the upper left corner is. Oh. Copy from reg. Okay, so we use... First of all, those two are unused. Well, I mean... Okay, this makes sense. Okay, registers. Now, I need to... Oh, and... What is this? R0, R0. This is instruction. And I think... Oh my god, why is it so spaced apart? Why is it so spaced out? Okay, fine. So we've got registers. Now, we need to... First of all, we need to decode an instruction. We need an 8-bit byte splitter for the instruction. Now, I can... Wait. I can move it out. I assume that's gonna just punish me for... well, yeah. What is the code specifications? Wow. Well, that's gonna be fun. Now, so we got an instruction. I think those 3 bits... So yeah, first 3 bits are the destination, I think. Yeah, those first 3 bits are the destination, and second 3 bits are the source. So we need a 3-bit decoder, 2 of those actually, and I'm glad they gave it back. So we've got source and destination here. This is destination, by the way, and this one is source, which, I mean, okay, they are a bit split. Also, the enable flag is inverted, which is interesting. But I mean, that means I can just leave it. So we've got source and destination. This one is source, right? Now the 7th bit. Oh, do we have? I have input enabled. That's useful. Okay, so we've got a long line running here. Maybe I shouldn't have crammed it all in this corner. Yeah, I should probably move it. Should probably move this somewhere like here. Also, it all just converts to one line. Much better, I guess. So the 7th bit is enabling this, not the 8th bit, because 8th bit is unused. Then we've got 6 other bits. So this is load. So yeah, I need to load one of them into a bus. So we've got a data bus here, which is cool. All I can say. here, here. Yeah, we've got a data bus here. Well, that's just selection of input. Now I need to connect. What? Why is it not letting me? Okay, sure. I don't care. This feels weird, but I guess. So yeah, the data bus means I'm gonna connect all the outputs of those things together, and so yeah, depending on which one is enabled, I'm gonna get the thing. Now, so the decoder, which is gonna let me select the thing I put the value to. Okay, this is gonna be this is gonna be problematic. 7th bit means output enable, which by the way connects to the data bus. Now let me also connect this to the data bus. I'm gonna do it this way because I like how it looks. For whatever reason, it does this weird curling around component thingy. That's sure. Now we've connected all the inputs. Now I just need a store enable. So the first register, get the second register, get this third register, get this. Now this is basically a simple computer without any arithmetic or logic operations. Okay, I think that's it, and this is messy. It did not improve. If there weren't spaced apart so much, it would have been more beautiful. But this seems to work. Oh my god. So what we do here basically, we just split an instruction into bits. Then first 3 bits, we decode them, and whichever register or the input we point to is getting enabled. When it's enabled, it's gonna output to the bus. And then the second decoder, which is the destination, is gonna enable the load on whichever register or the output enable from the bus. Whatever. Now what is this? Arithmetic engine. Oh my god, that's an ALU, right? So we've got the logic engine before, we did the logic engine before, now we're gonna get an arithmetic engine. Add addition and subtraction to your circuit. Yes. Did they? Oh my god, they restored my circuit. Or NAND, NOR, and sub add sub. Okay, can I NOR add sub? Okay, so if this one is enabled, we go to arithmetic mode, and if this one is enabled, we flip the bits. Okay, you know what? I know what to do. So I'm gonna select those two components. Wait, I couldn't select them to get. Okay, I just selected that, and I didn't select it properly. Alt click. Okay, now I can just drag a box around it. So now I wanna move. Okay, so now I wanna move this a little bit closer. Whatever. Now I wanna select the right thing. So either I select this by default. So this is just a logic operation that we had before, or we select another output, which is an addition. So first I'm gonna do addition and no carry yet. I wonder if it's gonna have the carry flag. I wonder if we're gonna get the carry flag in our thing. So yeah, no carry. We need to add those two inputs. Well, so we add the first one. I'm gonna try to carefully route it. You know what? I can switch to green for ALU operations, and also for arithmetic operations. Okay. So here we've got add, and before we do Where is the... So I'm gonna get negation, and I'm gonna get the a multiplexer. So before we just okay, so, yeah. So instead of just putting a normal a second input into the add, we're gonna negate it if this bit is on. So if this bit is off, we're gonna take this input and route it through. But first I'm gonna place negation somewhere close. So we're gonna take this input and route it through. Otherwise we take a negated input and then we route it here, and then it goes here, and it should work, right? Oh my god, we've got a manual entry on component factory. By the way, how small is this? This is pretty compact. I think I feel proud of myself. Onwards. Okay, I wanna see the manual entry. And we've only got one level to choose from, but next we're gonna have two, and conditions. Oh, we'll have a manual entry of that. An instruction decoder. Calculations program. Oh. Okay, component factory. Welcome to the component factory. This circuits you create in here will be usable as components in architectures. The circuitry you create defines the behavior of the component, and the layout defines its shape. Components can be added, renamed, or deleted. Okay. Oh my god. So this level allows me to create any custom components. How do I save it? Similar. No. I mean, I have an ALU, right? I wonder where I have probes. Wire probes? Memory probes? Huh. So that's some interesting IO stuff which we don't yet get to. We count rate register. So where do can I store? Okay, wait. How do it's so we have component preview. Okay. Assuming we can create components here. And we have an ALU. How do I save it? I think I can just exit out of it and it's gonna be saved. I mean, I don't think I can use an ALU inside of the component. Okay, hold on. I'm gonna go somewhere. Okay, skip the read. I wanna see if I can reuse the components. No, I can't. Maybe this level specific. It's also not giving me. Oh wait, switch schematic, maybe this one. Oh, ALU, I have components here. Okay, good. So I have an ALU schematic. Why can't I load it here? I have old custom. Maybe I can't load it on this level. Anyway. So I can actually create components here. So can you go away? Anyway, so let's go to this level. The circuit you build in the registers level can copy values between registers, while the arithmetic engine can do different operations on two inputs, but you need to be able to do both in the same circuit. To do this, build a decoder which will decode mode which will decode which mode our computer is in based on the 2 bits we haven't used yet. Continue. We have used 2 bits. Yeah, we've got 7 bits we've got 1 bit to spare. Why are you giving me 2 bits? To distinguish between instructions from 4 different kinds, the 2 highest bits will be used to determine which mode we are in as follows. By the way, I just wanted to check in Steam. Machine level using only components from the 8-bit category. By the way, I accidentally completed an achievement. That's interesting. But sure, that's good. So I wanted to check achievements here, just in case. Okay, so this one, for example. So So yeah, we've completed 4 NAND equals XOR last time, so we made an XOR gate out of 4 NAND gates. Now I wanted to so the product of nibbles is not, we haven't yet got to this level. Functions level, complete called conditions, we haven't yet done this. Complete the byte adder with a delay of 35 or less. I wonder how this works. Beat the level. Complete the counter level with a 65 gate score or less. Huh, I don't know what gate score is yet. But yeah, we could do a full adder one then. And I assume fast adder and a binary counter achievements. But yeah, I don't quite know how, because it didn't even show me the scores. I guess it's gonna be in the future. Anyway, to distinguish the instructions, here means any value. Determine the mode we're in from the input, then send 1 to the correct output. Well, that's just a 2-bit decoder, right? Yeah, quite literally, that's just a 2-bit decoder. Like, okay, fine, sure. Byte splitter. Okay, so I wanna know instruction. Hold on. Is there? Let me see the explanation again. Hey, that's not what I need. Decode the instruction. Wanna see the. Okay, let's. Wait, I can't replay. Oh no, I can replay level look. So 0, 0. Okay, those are last bits, right? So this is the second. Okay, yes, those are last bits. 8-byte splitter. Okay, now also I wanna switch back to the regular wire color. Now we just need to decode it. It's pretty easy, right? A decoder on here, a decoder. Where's another decoder? I mean, I could have used a 3-bit decoder here, to be honest, but I don't want to. Again. No, I still didn't get a multiplexer. But yeah, switches. I mean, yeah, I could have used a 3-bit decoder instead. This would have probably been more optimal. Now, just route this here, here, here. Wait, here. Now I select those two or those two. Now I just route this. I mean, well, that's simple, right? That's too simple. Your circuit has been saved to the component factory boot. Onwards. Oh my god, we're so close, by the way. Now we've got calculations and a manual entry. Also, component factory. Oh, I can click into component factory at any time. Also, it gives me the decoder here. I can place the decoder. That's funny. Now also, so I wanted to. I kind of want to do the achievements. Okay, let's do a full adder level using only 5 blue components. So full adder level using only. Okay, good. Using only 5 blue components. Okay. A full adder level. Are there not blue components? I don't know. Okay, so there is a way I can do. Is there a switch? There isn't even a switch yet. Well, is this and no, those are two, those are two, and those are two. Okay, so two XORs should probably stay. Now I need to determine if two or more inputs are on here. Maybe I could have used another XOR. So if two inputs here, one of those. Well, I mean, it's gonna replace another. It's gonna replace an AND, so that doesn't really matter much. Actually, I mean, we can invert the three inputs, but that's gonna take too many components. So, no. What could we do here? I think I can actually do it with ORs, you know. So I do ORs, and yeah, I switch to this color. So I do an OR here, connect those two, and then I do an OR here. Also, the size doesn't matter for this level. So if this one or this one and this one or this one, this one even does both. Okay, so we have one more component. She needs to have 4 inputs then. It's not gonna work. We have a half adder here. No, we don't have a half adder here. Okay, so we have a limit of 3 components on this. Also, it said blue components. I mean, all of those are blue, so... I mean, actually, no, those are red components. Okay. So when 2 are 0. So when those 2 are 0, we still need 3 of those. By the way, XNOR is just an equality, which is interesting. So both inputs are 0 and how do we do it the fast way, the small way? Check if any of them is a 1, but it's not helpful. And also, I could try do an AND. So for example, on those two, and if this one is 1, then this one is 0. We must do an AND, or if this one is 1, then we must do an OR. So I need to select, but I don't have the multiplexer here, and building it would be too much. So if one of those, depending on this input. I mean, I could replace an AND by a triple AND. And then that's not helpful. I can only imagine how to do this with four components, but I have a limit on 3. Okay, so I don't know. XOR. Inputs are different. I mean, I could XOR those two, for example. And this one. Or again, but that's not helpful. Probably like either triple ones or an AND or something. NAND, NOR, etc. XNOR maybe. Like chained. NAND is is 1 unless both inputs are 1. Actually, we can do 2 XORs and a check for 0. But that's not helpful. Because this is still 2 components. Like if I do 2 XORs, chain them like this. Just for example. So this is gonna be 1 whenever. Hold on, I have 2 XORs already. Hold on, actually. So only when sum is 0. Actually no. It's not working. I mean, I have an XOR here. By the way, I can reuse this XOR. So if I just do another XOR on those two, and then, so if either of this, actually I need an OR instead of an XOR. So I have XORs. Anything I can do with them? I could do a triple AND on the inputs. So if one of those are on, one of those, yeah, one of those must be on or both. And if both, then this one can be off or on. So if one of those is on, and I think I want one of those is on, which is XOR, and this one is on, then it's right. Or if both of those are on, or if both of, okay, I think we actually did it. So both of those are on. And then we do an OR here. No, I don't know why I'm packing so much. I think this is it. 1, 2, 3, 4, 5. 5 components. It's gonna work. It's gonna work. It's gonna give me the achievement. It's gonna give me the achievement. Let's go. 5 component full adder. Let's go. Now, anything else? 3 adder multiply. Well, we don't have this yet. And I think I know how. I think I know how we're gonna do this. But I'm not sure what the level is yet, so I'm not sure. So we don't have conditions yet, right? No, we do have conditions. Oh wait, that's the level we're on basically. So fast adder. Complete a byte adder with a delay of 35 or less. The byte adder. I mean, I don't know how to check the delay. So maybe later, and then binary counter as well. Complete the counter with oh wait, is this hold on, is the byte adder oh wait, no, it's not. This is like binary. The counter level with 65 gate score or less again. I don't have those metrics yet. And if I go back to this, yeah, I do have 255, so I guess I'm gonna get those metrics later in the game. Which means let's go here. Which by the way gives us a new manual page. Also, I write this is live. I don't know if you need this info. Time to merge in the arithmetic engine circuit you made previously with the register circuit. The calculation circuit was saved in the component factory and now can be added as a component. If you forgot which pin does what, check the circuit in the component factory. Use the decoder to to figure out if we should copy between registers or do calculations. Here are the 4 different modes again. Immediate mode. Calculate copy condition. For this level you only have to worry about the copy and calculate mode. Check the instructions. Oh, copy and calculate by clicking the gear on the top of the panel. Okay, so copy is once this bit is on, I mean, well actually, okay. And yeah, we do actually have spare bits. I'm mistaken. When calculate mode, take register 1 and register 2 as inputs and save the result in register 3. Okay, now we're gonna have to redesign a bit of stuff. An extra pin has been added to the register. This pin always emits the value of the register regardless of load selected or not. Okay, actually no, it's fine. It's fine, it's not, now it's easy, okay, fine. Okay, oh my god, we have so many buttons here now. Anyway, instructions. So immediate, I only need to worry about copy and calculate. And register 1 and 2. So calculate is those 3 bits. Copy and calculate. So they will have central data bus. Yes. No, it should be smart. Oh my god, this is so big. So many stuff. By the way, 8-bit counter, is it gonna be an instruction counter? Anyway, I'm going too far into this. Now we've got decoder and an ALU. Let me do a decoder and an ALU. Okay, so obviously we need to put a decoder in here. Also, it should probably move this somehow. And does it mess everything up? It kinda does, but who cares? Now we decode the signal first. Also, I should probably switch back to this. Now, um, I kind of want to do it. Okay, let me redo it. I really want to redo everything here. So we've got 3-bit decoders. By the way, we've got 6 registers in our imaginary computer. So those 6 bits. So I'm gonna move this down. I'm gonna move this down to the pretty much bottom left corner. So this one is the destination, this one is the source. Oh, it's the other way around. This one is the destination, this one is the source. Okay, I'm gonna do it two data buses now. As silly as this sounds. So this is the destination. Hold on, this is the destination. Yeah, this is the source. Now I route this here. So I don't like how this looks. So instead I'm gonna do okay, how to smartly route it. Well, obviously output enable. Oh, this one. Then I need load signal. So I'm gonna do a load signal here. Then I'm gonna do this, and I'm gonna continue like that. Right. So I'm gonna. I've seen this in a video, in a patch notes video. Like those lines. So this is much cleaner, right? It's like I could also like split. I could also make it an 8-bit input, an 8-bit bus, but this will not make any sense. So this is much nicer. Oh my god, this is much nicer. So this is the source, and the source bus we also need. I also need the source bus. Let me just do this. I'm just gonna do lines parallel like that. Oops. Here. Okay, now this is the output bus basically. Now let's do an input bus. This is gonna be more difficult because we can't really. Actually, no, we can do an input bus. So this is the value. Actually, I should have started from this one, but sure. Okay, so this is the input bus basically. I'm gonna route it here. Okay, this makes sense, you know. This is the input bus, and this is the bus that outputs values from registers. So I also need to do the same thing I did for stores, but for loads. I mean, so okay, the first one is the destination, right? Calculate, no, count. So copy from rec 5 to rec 3. So this is the 1 bit, and 2. Okay, yeah, right. Now I need this line to be separate, to go here. I'm just gonna route it like that. Now I want this line. Actually, Welcome back, Nigel. I'm redesigning this thing a bit. So we've got a task. We had a 6-register thing. We've got a task to integrate an ALU into that, and I'm redesigning the whole thing because I want it to look nice. And I think it actually does look much better now. Also, I should have moved those things further. Like that. Something like that. Okay, here. Here. I want it to look beautiful. Also, we've completed the Steam achievement once you were away. A 5-component full adder. So we've made a full adder with just 5 components. Okay, now this looks good. Now I need to actually select stuff, and this one will go here. Also, I need to buffer them all. Hold on. There should be a pretty parameter for the circuits. I mean, also we could put what instructions? Calculate. This is the instruction. Where do we store them? In register 3, right? Is it always register 3? 1, 2, 3. I think it is. Wait. Schematic. Overture. Oh my god. I think we spoiled the fact that this is the final computer schematic. So it better be pretty, right? Okay, now I need to be careful. So we've got an output selection thingy. Now we need an input a better input selection thingy. So I can hard code it and like put a buffer here possibly. So yeah, let's start integrating an ALU into the mix. So we need to add the values of those 2 registers and put it into the 3rd one. This is hard coded. So I think we put it into the input bus and then we take the 3rd one safe thingy. Using the decoder. Yeah, this could be the best way to do this. But then we need to disable all the loads then as well. I don't know how to do this. There are 6 of those. I need like a 6-bit buffer. Actually, I can... what? I can go to component factory. Switch schematic. And do a 6-bit buffer. We'll call it buff 6. Now let's so yeah, in component factory this has no area. How do I IO bidirectional pins, input pins, 8-bit input, 1-bit input. Okay, and now I put, so yeah, this is a component factory. Again, reminder, this thing is the it's gonna take so much space. 1, 2, 3, 4, 5, 6, 7, 8. So this thing is here so that we can create custom components. Also, how did they select it? I think it's like a hold mode. Okay, that's interesting. 1, 2, 3, 4, 5, 6. By the way, why did I make it an 8-bit one? Now I need switches. Look, this is messed up. Input, 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 output. Okay, also I should switch back to this one. Oh, and also I should add another I/O input. Can I rename it? Label direction up. Name label text. Enable here. Now I can switch color for this one. First I should probably finish those. I wonder if it's actually gonna fit. I wonder if it's actually gonna be smaller. No. So it all doesn't matter unless enable is true, otherwise it's just gonna be also IO output. It'd be switch output. Yeah, I should have done switch outputs instead. Let's replace 4, 5, 6. Let me replace those by those. Also, are those bigger? No, I'm imagining. Also, now I don't need switches now. I don't need anything. It's just it's just done by itself at this point. So I just route the outputs. And then I just route this. Now, component preview buff 6. Okay, can I save it somehow? How do I save it? I can hide this here. Now, as it has no area. How do I create an area? IO probe, switch, pins, custom old components. How do you define an area for a component? It didn't tell me. That's the most important part. Is there a manual entry on custom components? Oh, there is. Turn the shape. Different pins. Probes here. Folder structure, sure, but how do you create an area? How do you find an area? Anyway, I can define an area. I mean, there should be, there must be a way, but I don't know how. Might have to look it up somewhere. Complete component factory define area. Because like if I switch schematic to, for example, decoder, well, this has area, right? This doesn't have area either. Oh, actually, I mean, this is the area, I guess. Now, if I switch schematic to buff 6 back, hope it didn't, yeah, it didn't delete anything. Well, it's the same. It has no area. Maybe I should actually plug in some logic into it. I don't know this. Okay, this is the area. Like, this is what it means. Because I must have logic gates inside of it. I mean, I can have switches if you want. Okay, so if I switch back to this and remove this and get switches, I mean, switches are very unnecessary here, but I don't care. Also, this was an interesting visual bug, visual glitch. Oh my god, this lags. Should be able to do this. Just connect all of those, and for some reason it doesn't show me the space. So if the component doesn't have any logic, it's not a component, right? Wrong. I don't agree with it. Also, I deleted probably a bit too much. Maybe I shouldn't spend time here, you know. Well, I can delete the decoder, I can delete this. Okay, what if I switch back to the calculations one? Continue, close. And then I can... Oh, I can't edit folders here. Do I have a buff? 6 pins overlap. Okay, sure, I don't care. Then I don't care. Okay, so I need to multiplex. Actually, you know what? No, no. Okay. So I have I have two decoders. So I wanna make sure. Oh, we have a seventh. We have an unused seventh output here. Or input, whatever. Depends. So we could probably use that. Yeah, I'm gonna use that, you know. I can use that. So you can just hack into the copy command to use the LU thing, you know. That would be smart, right? Also, this is the final schematic. I just want to remind you, because as we can see here, overture. Okay, so frames by oh no, dropped 500 frames, 300 return lag. It should be back. Now calculation codes. So we need to have another stuff. With the decoder, I might not even want to use it since I have those two bits here. Okay, I mean, actually no. I have ALU and ALU. Now I want this output. What does ALU have? Instruction input 1, input 2. I want the output to be multiplexed into the bus, or actually like buffered. For the switch, I need a switch. Yeah, here's a switch. So the last one is gonna be the ALU. Yeah, I'm gonna do that. Hopefully they're not gonna change like it later. They're not gonna use it for anything. So wait. So this is the input. This is the input bus. Okay, maybe it's worth moving the ALU to the top. So just as a component. Now I'm gonna do this. I'm gonna do this, and I don't like how it looks. Also, I don't like this. Here, better. Now, I should put a switch in between that, an 8-bit switch. I mean, I could actually build this in real life, you know. So an 8-bit switch. Now we can route another line to that. It's gonna be the blue line. It's gonna be, yeah, it feels kind of weird, but that's how it is. So we're gonna route it to the switch. I'm gonna route it like that. Like that, because I want to. Now the ALU is gonna be enabled once this thing is gonna be enabled. So the first 3 bits are the destination. Yeah, so hold on, this is the destination, this is not right. I don't need this. I need the source. I need the source line. So I'm gonna do this instead. And now this messes up this thing. It broke, but okay, it's okay. We can do this. Okay, good. Now, I'm just gonna move this, route this here. Again, as I said. Now the ALU is gonna output once this 8th line is the 1. And the ALU, so the ALU takes an instruction and 2 inputs. An instruction is a byte, right? So one input is gonna be this. Okay, I'm gonna do arithmetic as this wire color. So this is the first input, this is the second input. Maybe I should make it more pretty somehow. Not sure. Not sure how. Because I can't rotate components, or can I? Level screen. Maybe this one could be. There's. Oh my god. Okay, that's probably a spoiler. Sorry. Okay, so I wanted to try take a custom component, for example, an ALU, and rotate it. I can rotate it, and it's gonna stay flipped. Oh my god. Okay. So many repeated frames. I've skipped just 47. Okay, let me change this. Okay, so I can rotate this component. I feel bad for a flipped ALU, really bad. But okay, I need this. Now I'm gonna take a switch and also rotate it. Also flip it. Which also feels a bit painful also. Yeah, I switch back to this for the data bus. Now I'm gonna take back the purple color. So this is a selection line. Should I color it differently from others? Oops. I like this one, or should I keep this color? I think I should keep it. Wire component, right? Wait. Oh, what? What was that? Or was it? Was it saying right comment, or and I just misread it? Refresh the page, I guess. Also it lagged for me as well. I feel like with latency you're gonna see it anyway. I guess it's just lagged a little bit. Okay, now the switch. Oh wait, I'm focused on the wrong. Now the LU is gonna be taking 2 inputs. Okay, now you know what? I don't want it to be rotated. I don't like it being rotated. I'm just gonna route it as is. Like that, and then I'm gonna route this here. And nail U is gonna take this as a first operand, and I'm gonna switch to the to the ALU color. Let's just say that. And then we're gonna also the instruction of the ALU. Now the decoder. So here we have a decoding part. Let me do this. So if have calculation and copy. This calculation is copy. Now if we're calculating, I need to so I need a multiplexer, right? So we have calculation and we have a copy. Oh, why did I do two? I don't need two. So we have a multiplexer, which is gonna take an instruction if it's copy. So this is, oh wait, this is calculation. If it's let's do a multiplexer on the data in out. If it's copy, this is a copy, right? Yeah, this is copy. If it's copy, we're gonna take this. Otherwise, I need a bit more than a standard multiplexer. I think I need 2 multiplexers with encoders. Actually, you know what? No, differently. We're gonna have this. We're gonna have a switch. Actually, 8-bit switch. We're gonna have 2 of those. Actually, okay, yeah, 2 of those per now. So the instruction that goes further is gonna be this. So I'm gonna move here. This is the instruction. This is the original instruction. Now I'm gonna do something like this. This is just a space where I can inject custom instructions, and I'm just move it here. Connect like that. So in case this is so we have what copy is this one. No, this is calculation. Actually, okay, so I'm gonna do this and this. This is the calculation one. Now I'm gonna inject custom code into this. Basically, we need ons and offs. So we need In order for the copy, we do 1 0 from full to register 3 exactly. 1 0 1 1 1 0 1 1. 1 0 wait 1 0 1 1 1 0 1 1. Can I? Oh wait, I can do this. Actually, feels weird, but that's really useful. Actually, forget. I could just do this. Oops. So yeah, this is the instruction in case of calculate mode. In case of calculate mode, so let me input the instruction. Calculate. Or actually, okay, let's do copy from input to register 1, register 0. Oh, actually, okay, well, we're gonna have to change it. Actually, can I alter the state of registers? I wonder. 1011. Wish I could transfer the instruction from here to here. It would be useful. But yeah, we'll have to build an assembly for that, an assembly language for that, and that's coming. So I can't impact it. Okay, so register 2 actually. And it's this. So 0, 1, and then 2. So I don't need this connection. Right. Now we do. Wish I could change it. Can I actually? No, I wish I could change it. Okay, fine. Now let's do an instruction. R0 R0 or condition R0 R0 3 7 question mark condition R0 R0. What is this? Oh, it's a copy. 1 0 from input. Okay, let's do from input. From input to R0, and then input is gonna be wait, I can't impact the input. No, I can. Okay, let's do 2 plus 2. Oh, this is 2. Okay, so this register gets 2 on the input, and the save is true. When is it gonna save though? Like, maybe if I toggle this, it's not saving the way. So we have 2. We have 2, but this wire is 0 for some reason. Oh wait, I don't have a connection. I don't have a connection between input and output. Hold on. But still, this, if this is 2 and this is enabled, this should be 2, right? Why this wire not 2? Not 2. Okay, if I connect this, I think it should be connected somewhere in a different place. So the 2 buses, the 2 main buses, I'm just gonna connect them now. So this is 2, I don't get it. Instruction. So when that happens, have input selected. Hold on. So this is enabled, right? This is enabled. Oh wait, I need to step. Ah, I forgot about that. Also 123. I don't want 123. Why is it 123? Oh, that's because it overwrote everything. Okay, let's step. And oh, like 1 and 2 instead of 0 and 1. Okay, let me redo this a little bit. Okay, let me oops. Let me take those and put them here, somewhere here. So actually here. So this register is an input, purple, and this register is an input, and the result is gonna go to the bus if enabled. So I'm gonna do condition this one. Control. Wait, I can draw like this. I forgot how to draw. Okay, so should I wire it all around? Maybe. Why can't I like switch the direction it's gonna face? Okay, like that. And now LU's instruction must go. Well, this is the instruction. I need the instruction to go to the ALU. You know what? I'm gonna do this. So that instruction is always available here, and I'm just gonna connect it like that. Now this should theoretically actually work. Register 3 is the result. Oh, also. Yeah, since register 3 is the result again, I should connect this. Yes, it works. Let's go. A basic computer. Look at that. It runs a simple, tiny program. It's not Turing Complete yet. It's not. It doesn't have instruction counter. It doesn't have instructions, etc. But still, unlocks a manual entry on instructions onwards. Okay, wanna know what it hides. So we've got a few more: program and conditions. So memory is little box counter. Okay, so those two will be. So those two, together with the computer we built, are gonna join and convert to a program. And then a conditions thingy, I guess, is the conditions, which are gonna make it Turing Complete on this level. So I guess let's do conditions first. So we'll have the value input and 3 condition bit inputs. A value input and 3 condition bit inputs. The 3 bits select the condition as shown below. Check if the value against the selected condition and output this if this satisfies and this other way. Bit code this is always false. This is value 0, this is less than 0, this is whatever, always again not equal to 0. Okay, so this bit is basically invert the value, invert the condition, because you know it works like that. Then we have equality, less than, and less than or equal to. Oh, so and those are just equality and less than. Okay, and you're just throwing me here. I have to figure it out myself. I mean, I know that I need to subtract, but like that's interesting. Okay, what the game calls an instruction, I want to read the manual entry. It's also known as an operation or an OP code, for short for operation code. Regardless of the operating system, programming language, or any other layers above it, software must inevitably be reduced to instructions for the CPU to process them. Internally, in modern CPUs, instructions are translated into microcodes which are even smaller steps out of reach for the programmer. Actually, no. ARM and other RISC-based architectures do not do that. They don't have microcodes. Anyway, so I need to decode the bits. Input is an 8-bit value. Okay. Need 2 bytes, split it. Breaks coming. Okay, now, when this is always never. Okay, so this is a flip bit. This is an equality bit. Okay, so I need I need a circuit that checks if a value is. Oh wait, it's not an equality, it's 0. Hold on. So this is a wait. This is a 0 bit. This is a negative bit. Negative bit. Okay. This is should be easy, right? Okay, I'm gonna split the value as well. This is just comparison. Comparisons. Actually, okay, yeah, it doesn't throw so much stuff at me. Also, I need a again. I need a 1-bit I need a 1-bit multiplexer, but they still haven't given it to me. I mean, I can make one myself, but you know what? I am gonna make one myself. Wait, I can't use custom components here. Never mind. Okay, let's do a decoder. So if this one is true, then we'd want to flip the output. Okay, let me do this and this, and then connect those, and then this, and then this, and then this. So this is a regular one, and then this is the inverted one. So I'm gonna put a note here. Hold on, why am I even doing this? I have an XOR gate. I'm dumb. I can just do an XOR. Not an XNOR, an XOR. Also an XOR is big. Is really big. Okay. Let me just connect this. I should probably do this instead. Now, this is a 0 bit and this is a less than 0 bit. So less than 0 is if this one is 1. Okay. This is gonna be ANDed or a switch. I prefer a switch. So if this is 1, so this is a less than 0 1. Okay, then a 0 1 is we have a big AND. Okay, let's we have a big OR. I can use this here, and another regular OR. So I need an 8-bit OR, basically. Okay, I'm gonna do this, and I'm gonna split. I mean, move this here. Just like that, like that, like that, like that. Okay, and then we're gonna do a triple OR again. Ideally, we would use an OR here, a triple OR here, but okay, we don't have that. Now let's just connect this. So that's an OR. By the way, can I move those? No, I can't. Sure. So if any of those bits are 1s, it's not 0 anymore. So we just invert this. Also, I should have probably... Okay, let me move this separately. So yeah, we just invert this and then we just put a switch on it. So this is 0 code, and this is less than 0. So let me do in blue for control lines actually. So invert also. Should have done this. Okay, so invert, then less than 0 goes here. and then equals to 0 goes here. It's a bit messy. I mean, actually, I will probably do this. Okay, should work. If value is less than 0, output green. Less than or equal to 0, output green. Value less than or equal to 0. This one is true. Oh wait, I forgot. I need an OR here. Yeah, obviously. And OR here. So I'm gonna remove those two. Yeah, let me switch back to this. And or those together, and then back to blue. So this one is less than 0, so this, and this one goes here. Right, now this should work. Silicon has been saved to the components factory. Yay. Manual entry on terminology? What? Instruction OP code memory address jump. Why? Like, actually, why? This is wrong. I shouldn't be given jump here, but sure, I don't care. Onwards. Now, we've got 2 levels left and we'll get to the computer. So, this is program. Okay, sorry. Yeah, I got too excited. So I think we should take a bit of a rest. 30 seconds is enough. Okay, that's done. Let's get back. So yeah, this one is exciting. And how long I've been streaming for? Because I think I might end here. Because yeah, it's a good enough point. We're gonna be building a whole Turing complete computer here in those 3 lessons, and this one is program is very important. It's like, you see how many levels are required for it, and yeah, we're gonna get programs, and we're gonna get immediate values and conditional jumps, basically. So yeah, and the working computer is gonna be here. Then we're gonna do a program, unlocks manual entry and something unknown. I think there's gonna be programming. Can't wait. But yeah, 2 hours and a half. It's 7 p.m. I mean, it's not that late. By the way, 11 followers by number. So yeah, I think we're gonna be ending. 3 viewers, enough. And well, yeah. Again, I wanted Turing Complete. I want to see if there's anyone doing Turing Complete. If anyone doing this with me. Nobody, unfortunately. Okay, then compiler. Compiler like that, just in case. Design again. Kernel. Okay, who should we raid? And all of those are my follows. Like, if I click following, nothing's gonna change. Yeah, that's funny. So yeah, No suggestions in chat, I guess it's latent. Um, I don't know, maybe Kevin. How many times we raided? Once in the last 30 days? Mixing multiplayer? Um, could also raid IRAD. Um, check YouTube. What? Yeah, I should probably check it more often. Read chat important. Oh. Um. Yeah, I do really need to get like YouTube API, but YouTube API is so awful. Honestly, YouTube API is so awful that I don't even want to touch it to integrate it. But yeah, sorry. So any rate suggestions? Yes, you don't really care because you don't need it. So by the way, Jake Blades, I think it's. Oh wait, that's a guy who named the stream, right? Uh, Including Cosmic? Probably no. I mean, fifth function maybe. T2, Christoph, Irad, Kavino. I mean, that's just a small portion of my fools. I'm not fooling Primogen. Sorry. Sorry, Primogen. Maybe someday. I need to watch somebody's stream for a bit of time before I can follow them. And I haven't really watched Primogen's streams that much. Anyway. So, any suggestions? Also, KickZ77. Oh, fair enough. Okay, I think I shouldn't stay here for long. Maybe we should support this function. He's playing something, and I think this also has a puzzle to some extent. Also, where's the sound? I mean, it might not have sound, but it's just so quiet that I think it's something up with me. Niles, but so yeah, thank you for joining. And I will see you next time, and by the way, so that you are sure I'm not gonna play it off stream. I'm gonna exit. Yeah. Join in next time because yeah, it's gonna be fun. We're gonna get to the Turing Complete. I think fifth function is the one who suggested me play that game. Might be. It might be. It might be like 2 or 3 people in total. Anyways, thank you for joining, and I will see you next time. Bye. It's funny.